Thank you for joining us for this really exciting conversation. It is really my pleasure to introduce Jack. Jack is the visionary CEO of Sandbox AQ, and he represents a rare combination of scientific insight, entrepreneurial prowess, and strategic foresight. And this has positioned him at the forefront of the quantum technology revolution.
Right.
So he successfully guided Sandbox AQ, which is a spin-out from Alphabet, and the spin-out was in 2022. And essentially, Jack transformed what was supposed to be a Moonshot project into a very promising enterprise SaaS company at the intersection of AI and quantum technologies. Jack's impressive background spans multiple disciplines. He had early success as a tech entrepreneur. He is an author, the author of Quantum Computing: An Applied Approach, which has become essential reading in the field. So let's welcome Jack to the stage. Jack.
Hi, Daniela. How are you? It's great to be here with you.
I am so excited for our conversation, Jack. First of all, congratulations on your Series E funding,
Thank you.
which completed just recently, right?
Yeah, we just announced it 10 days ago. Our second round, we had one round right when we spun out of Alphabet, as you mentioned, and we just did a second round, and together that's about $950 million. But what's great is not just the amount of money, Daniela, it's also the quality of the investors. Having investors who have a long-term horizon, having investors who really want to see progress in AI, used not just for large language models, but as you know, we're obsessed with AI for science, AI for chemistry, AI for new medicines, AI for new materials. This is the next wave, the next frontier of AI's impact. And the investors who joined us, Google joined us as an investor, NVIDIA joined us as an investor, Rowe Price, very large scale, long-term investors really believe with us that this is really the impact we can have on 80% of the GDP of the economy, not just the 20% in large language models.
So, Jack, it's just so exciting to hear you say this. And I'm wondering, how has your vision evolved from when you spun the company out to this point where you have raised practically $1 billion? And what will this money enable you to do?
Well, first I want to mention that right from the beginning, when we were inside of Google, one of the core bedrocks of our company is the ties to academia. And I think we'll come back to it maybe later in the questions. But I want to make sure we come back to the ways that we work with academia, because that informed a lot of the leapfrog that we did. Work here at MIT, collaboration here at MIT, collaboration with Misha Lukin at Harvard, just across the way in the physics lab there. These early collaborations when we were inside of Google really helped formulate the path that we took. A very, very different path, a contrarian path. The conventional wisdom, Danielle, as you know, at the time was, number one, 2017 was a famous paper by 8 Googlers. Anyone know the name of that paper, what the title of that paper is? Attention is all you need, right? And that paper set off a revolution. So the easy thing to do at that time was, let's go and build more transformer, based platforms. We said, that's great, transformers are great, but we also need other neural network architectures that would solve different kinds of problems, not verbal problems, not semantic problems, but problems when you train it on physics and engineering and chemistry and biology. And so that was the first contrarian thing that we did. When we spun out, we were only 11 people. Daniela, 11 humans spinning out. And today, thankfully, due to these rounds and due to the customer work that we have 85 PhDs, quite a few of them from here in Cambridge at various institutions. And we have 100 additional engineers. We have 185 very technical people in the company, and we have about 210 overall. So there's about another, 20, 25, 35 people who do additional things in the company. But one of the things we took away from being inside Google and our academic collaborations was to have a very technical team to really leapfrog in terms of where AI can go and also where quantum can go.
I really like your contrarian approach, because I really do believe that if everyone does the same thing, the world becomes incremental. So we really do need the new ideas. I'm wondering, you started with this powerful idea to go beyond transformers. Have you changed your vision or your approach along the way?
What we realize is that biopharma is where we started, and still is about more than half of our revenue today is from biopharma here in Cambridge. I just came from a meeting with a biopharma company. After this talk, I'll go to another biopharma company. There's a lot of activity in the biopharma world with AI that is quantitative AI. And I think that when people realize that language models, very helpful if you want to summarize scientific literature, very helpful if you want to do a marketing campaign or customer service. But when it comes to understanding molecules, and I brought one with me, any guesses in the audience what this molecule is? Any guesses? Related to the brain? No? Okay, there'll be more guesses later, I think. We'll see. But when you take a molecule...
What is it?
I'm not going to say. When you take a molecule, people can take a picture of it and figure it out later. They can show an AI and figure out the picture later. But when you take a molecule and you say, is this molecule that we're going to make in a lab as a possible drug, as a possible treatment, is it going to attach to a receptor in the body? Let's just say this is a receptor in the body. Traditionally, we've had to do a lot of experiments in a petri dish and then in animals and then in humans to figure that out. And 85% of the time, we're wrong. 85% of all clinical trials fail. And that's very expensive, both money-wise, but also to the patients. Patients lose out because that trial failed. What we realized, Daniela, and again, this was contrarian when we started this, is that on GPUs and TPUs, on the computers that we have today and coming out soon, we can actually do molecular work down to the electron level at scale, right? So each one of these atoms, be it a carbon atom or an oxygen or nitrogen, would have electrons around them, particularly the valence electrons, the outer electrons. And we can now figure out, using the laws of physics, whether these electrons will bind to each other at the interface of the chemical and the receptor. That was a contrarian statement only 5 years ago, was completely contrarian to conventional wisdom. We now demonstrated that, and we just have another world's record with NVIDIA in a paper that just came out and has been peer-reviewed and published in a peer-reviewed high-impact journal, demonstrating another world record in the ability to do computational chemistry at scale using a combination of physics-based equations and neural networks. Not transformers, but neural networks.
Yeah, I love that. I think, like you said, transformers have enormous opportunity for impact, but transformers also have limitations. In fact, in this famous paper, you mentioned attention is all you need. The third or fourth sentence says, we're going to do away with recurrences in order to facilitate parallelism.
Parallelization, yep.
So, and that's actually a very important statement. It points to the objectives for the transformer world, but it also points to some things that transformers cannot do. And in particular, loops, being able to look back in your history is very important for physics-based applications. And so I wonder, how do you think about the difference between the large language models that are based on statistics and more quantitative models like the ones you are developing?
Yeah, it's a fundamental question. You know, when you look at transformers and large language models, we predicted 6-7 years ago that it would become commoditized, that the general transformer model, which is trained on a very large data set, the World Wide Web, everyone has access to the World Wide Web. Everyone has access to understanding what transformers are. People were amazed that DeepSeek came out, and then Alibaba, Qianwen, and then Baidu came out with its AI. Anyone know what the Baidu AI is called? It's a very familiar name from Sesame Street, Ernie Bot. And so people were amazed. Oh my God, these companies are catching up. I don't know why anyone's surprised, Daniela, because the data is public, the models are public. You put the two together and you can create massive, massive, very powerful large language models. So there's all commoditization now in the large language models as predicted. There's no way to defend yourself with that traditional model. And what we realized is that we needed a whole nother tool set. And that's eventually what happens in every technology. You start with one major technology and then you realize that it's good for some things, but you need a wider set of tools in the toolbox. We train on data not from the internet. We don't use any internet data to train. We use mainly data that we generate from the equations themselves. We have equations in all the textbooks that tell us the interaction of an electron with another electron. We can use the parameters in those equations to take an initial molecule that may have come out of a lab here at MIT, and we can iterate on that molecule, make 100 million slightly different versions, permutations, Daniela, of that molecule. We can add a carbon ring, we can take one away, add a methyl group, take one away. And by the way, back to your question about what we realized post-spin out, we realized that these same questions were being asked not just by the biopharma community, but also by material science, by automakers, by space, by Airbus and Boeing, people who want to make their cars lighter, their airplanes lighter to get more fuel efficiency, folks who want a new kind of material to make new kinds of tools out of. And there's a lot of material science happening right here at MIT, and we're starting to collaborate on that basis as well.
So all that requires physics, right?
Yes.
And we have to go beyond statistics.
Exactly. We have the equations, and now we can do it at scale. We actually had to work with the chip makers to enhance the libraries that are inside the GPUs, the firmware, and allow the GPUs to understand not just graphics, the G in GPU, not just large language models, but to understand physics itself. And you may see some new libraries in CUDA now. Q tensor, CU tensor, this tensor that we're talking about, are the tensors that we use to represent physics, quantum mechanics, and also neural networks. Tensors are very powerful mathematical abstractions that we use in our fields to make this happen. Q quantum, CU quantum, is another library in CUDA that we and others worked on that allows us to bring quantum equations into the GPU world. And this, again, Daniela, was contrarian to conventional wisdom. Conventional wisdom said we have to wait for a quantum computer to do this work, and we demonstrated we can do quantum work on GPUs.
Yeah, no, that's extraordinary. I like being on the contrarian path alongside you. But I do want to ask you, how do the principles of physics and chemistry and other physics-grounded sciences impact the next breakthroughs in AI? Where do you see the field going?
Yeah.
Enabled by these physics-based models, perhaps even working together with large language models?
Yeah, I do think there's going to be a synergy, already is a synergy between LLMs and LQMs, language models and quantitative models. Physics we can think about in a very abstract way as one of the most powerful modeling tools that we have in our human toolkit to understand the world around us. Physics initially was asking, what is the world made of? Atoms and, different, the standard model, basically, photons, so on and so forth. But physics also goes beyond just asking those very core questions to asking, what are the best tools to model something as complicated as the universe? And in quantum mechanics, this is how we got to the Hilbert space. This is how we got to these super high dimensional and sometimes even infinite vector spaces. These spaces are very, very powerful. Linear algebra, which is not taught enough in our K through 12 schools, is the basis both of what we use in neural network lab and what we use in quantum mechanics. And there's a reason why we use linear algebra in both these disciplines, of course, because it's the most powerful way we can represent a high-dimensional system. And high-dimensional could be, for example, in the transformer model, a high-dimensional way to say, let me look at a paragraph and let me parse that paragraph down, and I'll put words that are similar on this route or that route, or even a recommendation system from Netflix does that for movie recommendations. But we can also use these powerful representational tools for the high dimensionality of where a molecule is going, of what a material will be. This high dimensionality can even extend into quantitative finance, because there you don't have molecules, but we have portfolios. and portfolios themselves could be represented in this high dimensional space. So this is an area, I think you would agree, Daniela, that is fertile for further work and impact in the world.
Well, so as MIT geeks, we just love to hear that there is a world out there where traditional AI comes together with these physics-based AIs. So what does this enable? Can you talk a bit about
Can I give some examples? Yeah.
your customers or ways in which you're using this?
Well, I want to give you some concrete examples. In addition to, of course, biopharma work, where it's very clear we need to make medicines for Alzheimer's. There is no good medicine on the market today for Alzheimer's. There's been 2 phase 3 failures in the last 6 years in Alzheimer's. When we look at dementia, when we look at ALS, another famous actor was just diagnosed and reported out himself, Eric Dane, that he has ALS, a devastating disease. We need treatments for cancer. While we've made a lot of progress on breast cancer and some other cancers, we have yet to make any good progress on glioblastoma, brain cancer. I started my career, Daniela, as you know, as a medical scientist at NIH, bringing together physics, neuroscience, and AI in one lab. And I had the privilege of seeing the initial results there, but we need to go so much farther. But let me give you even another concrete example of quantum and AI coming together. People may know quantum computing, they may have heard about it. You mentioned that I wrote a textbook about it, which is used here in this university and other universities. But let me actually talk about another aspect of quantum, which is quantum sensors. And quantum sensors are here today. We don't need millions of qubits. We don't need error correction. They're self-corrected. And quantum sensors can sense the world around us in a way that classical sensors cannot. There's only one problem. They're so good, they're so sensitive that too much information comes out of them. And so,
can you say what kinds of things can they sense?
Right now at the Mayo Clinic in Rochester, Minnesota, one of our sensors is there detecting not the electric field of the heart. That's known as what? When you EKG, right? EKG is the electric field of the heart, electrocardiography. But instead, we're detecting another field. Faraday taught us that every time there's an electric field, there's also what kind of field? A magnetic field. And so it stands to reason that if there's electricity pumping the heart, which is what causes the contraction of the heart, there's going to be a magnetic field of the heart. And indeed there is. And the sensor stack that we made is at the Mayo Clinic right now in the emergency room of the cardiac hospital. And as people come in with chest pain, we're detecting how their heart's doing in under 5 minutes, not looking at the electric field, but looking at the magnetic field of the heart with a quantum sensor, going to a GPU, going to our AI model, a quantitative model, LQM, looking at the heart's magnetic signal and determining in under 5 minutes the kind of heart attack this person's having. This is a revolution as it gets approved that will affect cardiology in the whole world. This is something that is the melding, Daniela, to your point, of AI and quantum coming together. You can't do one without the other.
So can you explain to us why sensing the magnetic field with this quantum sensor is actually better than using EKG?
No, thank you. So if someone had his EKG here, I'm sure many of us have tried it. The wires are there from the machine, and they have little pads that ultimately will, especially for guys, it hurts you when you have to rip it off. And these are detecting your skin conductance. And your skin conductance is very indirectly related to your heart, right? Those wires are not on your heart itself. They're on your skin. But the magnetic field comes through the cavity of the body, undisturbed, unperturbed, intact in 360 degrees around us. That is a beautiful, pristine, high-density information view of the heart. Unlike the EKG, which is very indirect and often has many false positives and many, many false negatives. So now we're talking nearly about a channel of data, of information flow, back to Shannon, back to information theory, that we can detect and we can now use for clinicians, and we can do so in ways that are far better than an EKG.
So why do we need quantum for that?
So that's a great question. The magnetic fields we're talking about for the heart, and by the way, roadmap alert is that next we're going to the brain. The brain also has electricity. We know that the way neurons communicate with each other is electrochemical. and that electro part creates a magnetic field. And there's always been a field of EEG, electroencephalography, which is very limited, again, in nature. But MEG, magnetoencephalography, can take us a whole new way because it's three-dimensional and also real-time. These magnetic fields are very weak, very, very faint. If I take a paperclip to a real magnet out here, it'll stick to it, it'll be attracted to it. If I put it to my chest, it'll just fall down. Magnetic field of the heart is not strong enough. So we need really good sensors to get into the brain and the heart and really pick it up the minute differences. But again, the contrary part to that is that it's so much information, no human could absorb that. And that's where we need AI. We need quantitative models to understand.
Well, that's really awesome. So what else are you working on besides these heart magnetic sensors?
Well, in addition to heart magnetic sensors, another synergy, another convergence of AI and quantum has to do with another whole field, and that's navigation and detection of the world around us. Today, we mainly navigate with a technology summarized in 3 letters. How do we navigate today? GPS. And GPS depends on satellites. And satellites are brittle. And the satellite feed that comes to our phones is well known and publicized. It has to be, because Apple needs to know how to tune your phone to receive this GPS signal from multiple satellites. That means it could also be jammed. In fact, multiple countries in the world are jamming GPS right now. And so when the Azerbaijani flight took off a number of months ago and unfortunately was shot down, partly why that happened is that they did not have GPS, Daniela, from the beginning of that flight. They inadvertently moved into Russian-controlled territory. And I don't believe that that morning anyone in Russia woke up saying, let's shoot down a plane. I don't think that happened. But they moved into a field that had an automated anti-aircraft artillery and got shot down, and those people died. So GPS is really important. It's fundamental. And unfortunately, it's very brittle and very easy to jam and even spoof. We have developed a technology at the interface of quantum and AI to use quantum sensors to detect now not the magnetic field of the heart or the brain, but in this case, the magnetic field of the Earth. And that magnetic field, because of the crust that we have on Earth and the distribution of minerals on Earth, is unique on every square meter of our Earth. Every square meter has a unique fingerprint, just like our fingers do, that tells us where you are. Satellites have taken pictures of them in a map, and we now have those maps. So again, a quantitative AI, not a language model, can look at what's under the plane in real time and what the map is, and tell the pilot, hey, pilot, here is where you are on Earth. And this requires no satellite, no connection to the outside world, cannot be spoofed or jammed. So this is a revolution now in the navigation area using similar technology that we just discussed.
Jack, this actually gives me a good bridge to my next question. I wanted to get your thoughts on how your company collaborates with academia. And when you talk about navigating using the Earth's magnetic field, this is, I get really excited because we actually have a project as part of our AI accelerator program that is looking at this problem, not with quantum sensing, but with other tools, with physics-based AI.
Yeah.
So let's talk about it. But more generally, what are your structures for engaging with academia?
Well, I'm glad you asked about that because, by the way, I have my periodic table socks on with me. I don't know if people can see that, but extra credit for those people who can know which elements are these.
Very cool.
So right from the beginning, when we launched Sandbox inside Google initially, and the AQ, of course, stands for AI and quantum, we realized that we needed to be at the cutting edge, both from an industry perspective, but also with partners in academia. And when I started hiring PhDs from the top universities, I realized that they're super smart, super capable, but during their academic career, they had not been exposed yet to the kind of things we did at Google, writing code that 7 billion people would use every single day, code that is reliable, that is mission critical. Very often, if you're doing your thesis, you're writing code, but you use it, you demonstrate it, and you probably don't return to that code very often. You don't put it in front of 7 billion humans a day. And so what we realized is we could offer value to the university by working with the faculty advisors, with the masters and PhD students, to bring them into our organization for 3 months or 6 months or even a year or two in the case of postdocs, and provide them with training that is complementary to the training they get here in the academy. And we started that 7 years ago, and I'm very proud to say, Daniela, with your help, with the help of many other collaborators in top universities, we've now trained more than 575 PhD and master's students around the world. And we've done so with the collaboration of faculty advisors like yourself. We've done so in fields of AI, chemistry, physics, mathematics, cybersecurity, many other related fields as well. And we've done so bringing them into a multidisciplinary environment. The 85 PhDs that we have serve as an unofficial co-advisor to the faculty advisors. We have a beehive of activity across these 7, 8 different disciplines. We don't have the traditional boundaries. One beautiful thing about CSAIL that I love working with is that you don't have the traditional, departmental boundaries, right? The silos. So CSAIL to me is so excellent and productive in part because it's not a traditional department in a university. And so that's what...
contrarian.
Yes, that is very contrarian. And you also have industry partners as well, which is not the usual case of many universities. So we started this program called the Residency back at Google. We spun out with it as well, and we now have expanded it. We're doing 100 residents a year from universities around the world, and we now do full postdocs on top of that. And what's beautiful about residency is that we can give stipends and pay very well to help the students with their education, but we return them back to academia to finish up their PhD. And then they might go to work at our company, they might work at Google, Amazon, Microsoft, other industries, finance. We like that because we're putting our alums out into the world, we keep in contact with them, and then they often come back to academia where they may become professors at CSAIL or other places, and then we do collaborations. Last year, Danielle?
We gotta have her upstairs.
Okay, we did 18 papers with academia, so it was wonderful.
Amazing, Jack. Sounds like such great impact, both on the technology side, on the business side, and on the education side. And as we say it in AI, I hope you can keep the gradient.
Yes, exactly. Thank you, Daniela.
Thank you, Jack.
Excellent. Thank you, Daniela.